Okay, welcome back. There was a homework from page 244. It's the last homework from chapter 5 on the inclusion-exclusion principle. And some of these problems are really hard. Here it is, 7, 8, 11, all the way through 24. Let's go. We're just going to do all these problems right now. Okay, number 7 says, suppose the letters A through J, so A, B, C, D, E, F, G, H, I, and J are how do they put it? Arranged randomly in a string. Okay, so just some string of length. How many letters are these? If you count them, you will see that there are 10 letters here. So make a random string out of these 10 letters, string of length 10. Prove that after removing up to 6 well-chosen letters from the string, the remaining letters will either be in alphabetical order or else will be in reverse alphabetical order. Okay, so alright, just to take a arbitrary string, so okay, D, G, I, C, A, F, oh my god, why did I do this? I did already. A, let's just go now, B, and oh my god, what's left? E, F, so we'll do F, E, G I got already, and then H and I, H and J, so we'll do J, H. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, because I'm dumb, and I'll put the H here. Great. Claim of Gossett is that you may, by removing 6 letters, produce a string which is in alphabetical order or reverse alphabetical order. And yeah, we can just do this, right? One thing we could do is A, B, E, H, or E, J, I mean. And is there even another one? I bet there is. I don't care. Yeah, C, F, H, J also works. Okay, so what's going on here? What's going on here is really, this is just saying that given this string of length 10, that there is a substring of length 4 in which the letters are all in order or not in order. So hopefully you immediately recognized that this is just an application of the theorem that we proved from this section, that given n squared plus 1, we phrased it at the time as numbers in a sequence, but I think even during the extended video of this, I mentioned that they really don't need to be numbers, and they don't even need to be 10 consecutive numbers. All that matters is you just have 10 things that are linearly ordered in some kind of a way. Then there's always there's a sub-string, or in the video I called it a subsequence, but okay, a subsequence of n plus 1 of them, which are always monotonically increasing or monotonically decreasing. So this is an example of an application of that theorem in a perhaps slightly unexpected context. Because of course removing 6 letters is the same thing as saying that there just exists a substring of length 4 of those letters which have to be in order, either reverse or backwards. Okay, so that's all I have to say about that. Boom. 8. What is 8? This is a controversial problem because I think that there was a typo, and so I noticed it's a fun thing to do because about half of the textbooks that seem to be out in circulation have one number printed and half another. So here is what it says. For example, in my very own textbook, it says, I'm going to write this out in full, consider the set, and then it says take all the numbers 1, 2, all the way up to 10, 11. So take the numbers from 1 to 11. This is what it says in my book that I'm holding right at this moment, and possibly in your book as well. Show that if any 6 of the numbers are chosen, then 2 of them will add up to 11. Show that if any 6 of the numbers are chosen, then what did we say? Then 2 of them will add up to 11. Then 2 of them will add to 11. Okay, well, as stated, this is just obviously false, because I can easily find 6 numbers such that no 2 of them add up to 11. For example, I take, I don't know, 6, 7, 8, 9, 10, and 11. That is 6 numbers, but no 2 of them add to 11. So this theorem is just false as stated in my version. In other versions of this book, the problem has been corrected to say, consider this at 1, 2, all the way up to 10. Show that if any of the 6 numbers are chosen, then 2 of them will add up to 11. And now we have a true statement. How do we prove this? Classic pigeonhole principle situation. We say, okay, well, what kinds of numbers add to 11? Well, 1 and 10 add to 11, so just like put them in a box. 2 and 9 add to 11, put them in a box. 3 and 8 add to 11, put them in a box. 4 and 7 and 5 and 6. Okay, and so here we have 5 boxes, and yet we are choosing 6 numbers. So by the pigeonhole principle, if we choose 6 numbers and every number is accounted for because now I've fixed my set, so it's only the numbers up to 10. And so I've partitioned the set of numbers into these 5 boxes. And so if the 6 numbers must fall in these 5 boxes, then the pigeonhole principle says that there must be 2 numbers in a box. And so one of these boxes has 2 numbers in it. Well, these boxes have been constructed such that the sum of the numbers in any given box is 11. So there it is. Okay, cool. 11. This is also just a repeat of a problem we sort of did already. So I'll do this kind of quickly. What is number 11? It says, prove that in every set of 1001 real numbers. Ooh, real numbers. Missed you guys. It's been a while. From the half open interval 0 to 1, that at least 2 of the numbers will differ by less than 0.001. Are chosen, so I'll just write are chosen from then. So if 1001 real numbers are chosen from the set from 0 to 1, then at least 2 of them will differ by how do they phrase it exactly? Less than 0.001, which is just 1 over 1,000. Okay, and well, the way to do this is exactly like what we did in class. We just partitioned the real number line from 0 to 1 up into subintervals. And so you take everything from 0 to 1 over 1,000. And then the next subinterval is everything from 1 over 1,000 to 2 over 1,000. And then everything from 2 over 1,000. Man, my board is too small. And then you keep on doing that until you get to the final partition of the interval of real numbers 0, 1, which is going to go from 999 over 1,000 to 1,000 over 1,000, which is just 1. Okay, so we have now a partition of this interval such that every single real number falls into exactly one of these 1,000 subintervals. And so if we now choose 1,001 real numbers, then the pigeonhole principle says that the 1,001 real numbers chosen, if we have only 1,000 subintervals, then there must be two numbers in the same subinterval. And so one of these subintervals must contain two numbers, but these subintervals have been constructed such that they have a width of 1,000. And so if any two real numbers fall into the same subinterval, then those two numbers are less than 1,000 apart from each other. Okay, good. That was 11. And 15, I just did already in the video that introduced the pigeonhole principle. Because it was just an obnoxious and tedious example of the pigeonhole principle being used, so I just did it in that video. And here we have another obnoxious and tedious application of the pigeonhole principle. But as I stressed in the other video, it's you sort of have to give a really, really hard example for it to start being worth your time to apply the pigeonhole principle. Because if the problems are so easy, then you just do them using your wits. So I support this pedagogically, although it doesn't mean I want to do this problem. Here we go, just giant paragraph. This is so gossip. A 7th grade math teacher, this is number 17, a 7th grade math teacher decides that she would like to treat her 2 classes by bringing in ice cream. Aww. She does not want to have to worry about bringing in ice cream toppings, so she chooses 3 extremely flavorful types of ice cream as candidates. Alright. Strawberry blackberry cheesecake, chocolate caramel brownie, and toffee fudge swirl. No type A, B, C for gossip here. She conducts a survey of her 79 students by asking them which of the 3 candidate ice creams they like. And then here we go. Alright, so just so annoyingly titled. But let's go. Let's let S be, let's let S stand for strawberry blackberry cheesecake. Strawberry blackberry cheesecake. These certainly are some flavorful ice creams. And let's let C be chocolate caramel brownie. Chocolate caramel brownie. And finally, let T be toffee fudge swirl. Toffee fudge swirl. Okay, so continuing the conversation, what happens? She conducts a survey of her 79 students by asking them which of the 3 candidate ice creams they like. 38 students claim to enjoy blah 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 blah. Interestingly, 5 students claim that ice cream is their favorite food. Immediately on, so just say they just like all 3. Okay, so basically the big picture here is, in order to please everyone, she wants to pick some ice cream flavors such that at least one person will be happy. Sorry, that everyone will be happy with at least one of the options. So this is a kind of a reasonable type thing. And the final questions that will sort of guide our analysis are, how many of the 7th grade students like, how many, well, they ask weird questions, in fact. So let's ignore that. But our sort of overall question is, what is the relationship between the number of students who say, so the way this is done is, you're presented simply with these options, and you just say yes or no if you like it or not. And so you might like just strawberry blackberry cheesecake, or you might like these 2, or you might like these 2, or you might like all 3, or whatever. Okay, so good. So really, S should refer to the. This is really the set of students who like this flavor. Let's let our S refer to that. The set of students who say that they like this flavor of ice cream. Okay, now let's translate his kind of tedious prose into an analysis of this problem. Step 1. She conducts a survey of her 79 students. Okay, so there are 79 total students. And notice that, like the other problem 15, we have to be a little bit careful because it's possible that someone might not like any of these 3 flavors. Okay. Next, 38 students claim to enjoy strawberry blackberry cheesecake. Okay, so the size of S is 38. Next fact. 20 students report to disliking chocolate caramel brownie. Okay, so if 20 dislike chocolate caramel brownie, then the size of the sort of complement of C is 20, which I will just translate into, therefore, 59 must actually like chocolate caramel brownie. That's pretty high. Next. Oh, this sucks. Good. 29 say that they do not enjoy toffee fudge swirl. So the complement, once again, of T is 29, which means that it must be the case that 50 people do like toffee fudge swirl. Oh yeah, good. Additionally, 26 students say that the flavors of strawberry, blackberry cheesecake, and chocolate caramel brownie ice cream are good. Okay, so what he's trying to say here is that S and C, this number of people who like both of them, so S intersect C, is 26. Good piece of information there. And 17 students are fond of strawberry blackberry cheesecake and toffee fudge swirl. Strawberry blackberry cheesecake and toffee fudge swirl, so they like both of them, so they're in the the intersection of those 2 sets. That's 17. Okay. Interestingly, 5 students claim that that ice cream is their favorite food and believe that all 3 candidate flavors sound wonderful. Okay, so that means that they just like all 3 flavors. So S intersect C intersect T is 5, and then a few students, 2 to be exact, say that they dislike all 3 of the teacher's ice cream options. Okay, that means that of the 79 students, 2 just don't like any of these. Maybe they're just vanilla kind of people and they don't like all of this flavor. Therefore, by taking the complement, we see that 77 students like at least one of these 3 flavors. And so S union C union T is 77. Okay, and now we've done the hard work of translating, I think we have, of translating all of this analysis into math language. And now let's see how far we can get with just making a picture. So what's the picture? The picture is like this. We assume that there are, we have these 3 sets, and we assume that there's kind of some overlap between them until we learn otherwise. And then we try to just sort of fill this in. Well, here, contrary to the previous problem, here I can kind of make some progress. So if this is S, and this is C, and this is T, and we might find that we can just do this using our wits, and we don't need the inclusion-exclusion principle. Let's see. 5 goes here, so that's kind of nice. And what about S intersect T? S intersect T is 17, so that makes this 12. And also, so I feel like I used that fact. And then also S intersect T is 26, which means 21 goes here. Oh man. Wait, have I done this all wrong? No. And then C intersect T is, I don't have that one. So wait, what have I used? S intersect T is 26, so I've now used these 3 facts. And now, let's see, S is 38, so that's 17 and 21 is already 38. So that means there must be none that only like strawberry. That was kind of surprising. But now, do I hit a wall at some point? I a little bit hit a wall now. I know that the total number, okay, it's very likely that a smart person with a little bit of effort could just finish it from this point. But hey, whatever, it's a discrete math class and we're learning about the pigeonhole principle, or the inclusion-exclusion principle. So now let's sort of fall back on that formalism to help us guide us through this. Well, what do I know? I know that Is this what I want to do? Sure. I know that S union C union T, this is what this says, is going to be equal to, well, it's going to be S the size of S plus the size of C. So all the people who like strawberry, all the people who like caramel, plus all the people who like toffee, but then minus all the people who like strawberry and chocolate, caramel brownie, because we double counted them in this analysis, minus, I'll just stop talking and just do it, S intersect T minus S intersect C, and then finally plus S intersect C intersect T. And so actually this is, I think this is not so unreasonable to just do this analysis. It's not really that hard. So let's go. What is all this? This I know to be 77. This I know to be 38. This I know to be 59. This I know to be 50. This I know to be 26. This I know to be 17. And this I know to be, oops, I did something wrong. S intersect C, S intersect T, and this should say C intersect T. And is that maybe just like the one I don't know? Yeah, that's just like the one thing I don't know, is C intersect T. And so I'll call that X, and this one, the intersection value is 77. And so this whole thing now turns into this equation. 77 is 38 plus 59 plus 50 minus 26 minus 17 minus X plus 77. And if you do this all out, I guess you get that X is 32. Okay, so what does that tell me? It tells me now that C intersect T is 32. Well, if that's 32, then I know, going back to my picture, which organizes things visually, that this is 27. Whew. And if that's 27, then here we get 32 and 12 is 44, but this is size 50, so it must be 6 people who don't like this, and here, now I'm panicking that my math is wrong. Let me just do something here and double check this. No, I guess it's just good, right? 147 minus 43. This is not 77. This is 5. That's 77. All right. 5. So that was a mistake, and then that's 5. But now I think this math is right. I'm checking it on my paper, and it looks pretty good. 144, 5, 104, and then 32. Yeah, okay. So good. So anyway, what's left to figure out? Just this last one. This is 26 and 27 is something 53, but C is 59, so there must be 6 here as well. Okay, and now I've sort of done, there's sort of like a 5-step process. It's sort of read and understand the problem, establish some sort of notation to keep track of what's going on, carefully reading through the paragraph, translating the prose into mathematical language, making a picture to guide us. It's possible that they gave us enough sufficient information such that I could just make the picture, but getting stuck at some point, then using the inclusion-exclusion principle to solve for the sort of missing term seems seems like a good way to do it, and then sort of fill out the rest of the picture. Now I'm prepared, now that I know everything, I'm prepared to answer Gossett's silly questions, which are, how many of the 7th grade students like both chocolate caramel brownie and toffee fudge swirl? So they're asking for C intersect T, which that was the thing I solved for. That's 32. So the answer to part A is 32. And the next question is, how many of the 7th grade students who like at least one of the 3 candidate flavors? Okay, so never mind these ice cream haters. Let's take just the 77 people who like at least one flavor. would be disappointed if the teacher brought in toffee fudge swirl. In other words, how many people don't like toffee fudge swirl from among the people who like at least one? So this is going to be the complement of T. So it's 27 is the answer. There are 27 people who like strawberry or chocolate but don't like toffee. Okay, whew, good. That was what I will call a kind of a basic inclusion-exclusion problem. Now suddenly it gets, oh no wait, then there's another like weird problem. 19, eh? Oh, this problem is stupid. I'm sorry for assigning it. Let's just do it really fast. All right. For all you people watching at home, these videos could be better, but they could be worse. Woo! Okay, 19. We do it. What does it say? It says consider the set S, where S is in fact the union of 5 sets. A1 union A2 union A3 union A4 union A5. And so we go. Use the inclusion-exclusion theorem to generate a formula for the number of elements in the union of the 5 subsets of S, given that no 3 of the sets have any elements in common. Okay, I really don't know exactly what the hell they're talking about here, unless it's just, dude, I think what they want me to do is just tediously write out, well, this is going to be all the things in set 1, plus all the number of elements in set 2, plus the number of elements in set 3, plus the number of elements in set 4, plus the number of elements in set 5. Minus all the things which are in A1 and A2. Minus all the things which are in A1 and A3. Minus all the things which are in A1 and A4. Okay, and now a reasonable person would start rebelling here, or using notation, which is really the same thing. Deep thoughts, and realize that this is just, what we're doing is we're just taking every possible pair. So actually, maybe we should give Gossett some credit here, and maybe that's what he wanted us to use is notation in the first place. In other words, that S is just the sum from I equals 1 to 5 of the size of A sub I. Yeah, this is probably what he wanted. Minus, and now we get to be fancy. So now we go from I, what do I do? Like this. 1 less than or equal to I, which is less than J, all the way up to 5. Fancy. Of AI intersect AJ, ka-cha, ka-cha. And so what we're doing is we're taking every pair of numbers between 1 and 5, where one number is definitely larger than the other, and well, we're taking taking their intersection, and this is what the inclusion, and then we stop. That's it, because he has told us explicitly that there are no objects which are in 3 sets. So that just terminates it right there. So that's kind of nice. Okay, good. That was 19. All right, the rest, then the next 2 problems are, in my opinion, so hard. And this is one of those situations where some students figured this out in previous years, and I sort of wrote it carefully down. A couple of years this took the entire class kind of working together and talking it all out to make some sense of this. So if you really tried this problem, I would be very impressed if you just got it using your own wits, because I just do think it is so hard. And this also seems practical in a kind of a sense. Like, I could imagine this being an important thing you might want to investigate. Okay, and this is something I don't think we've talked about yet the entire year. Bitstrings. And actually a lot of combinatorial proofs can be accomplished by just considering arguments involving bit strings. What's a bit string? Okay, you guys all know this. It's just like a string of zeros and ones. And here comes the question. Use inclusion and exclusion to calculate the number of bit strings of length 7 that do not contain a sequence of 5 consecutive ones. Okay, so that's our task. We want the number of bit strings of length 7 that do not contain a sequence of 5 consecutive ones. Okay, well that sounds really hard. So, what we will do is consider the complement. Switch to a new marker. And what we will do is we will say, okay, well, let's consider all the bit strings of length 7. So all the strings of length 7 where each character is either a 0 or a 1, that's what a bit string is. How many of those are there? Well, there are clearly 2 to the 7th of those. And now let's subtract out the number of bit strings that do contain a sequence of 5 consecutive ones. Okay, this seems like it would be easier to count. And yet, counting the number of bit strings that contain a sequence of 5 consecutive ones is actually quite hard, I think. Because now we can sort of just imagine, well, what does a string look like with 5 consecutive ones? Well, one possibility is, if the string's of length 7, one possibility is that it looks like this. So 3, 4, 5, 6, 7. One possibility is that the ones are all in front. So it looks like 1, 1, 1, 1, 1. And then I'll leave those last 2 blank because, well, I don't know anything about those last 2. Okay, and so this is this is one way that bit string could look. And yet another way that bit string another way that a particular string could have 5 consecutive ones in it is if the middle 5 were all ones. And another way for this to happen is if the final ones were all ones. Okay, so I'm performing a sort of case analysis on strings of length 7 that have 5 consecutive ones. Either the first 5 are ones, or the middle 5 are ones, or the final 5 are ones. But now we see, and I'm going to refer to this type as type A, this type is type B, and this type is type C. And so I want to know all the strings which are either of type 1, or of type B, or of type C. Well, it's easy to calculate the number of strings of type A, because if you insist that if that was the entire problem,